In this video, I'm going to use example to show you how to run and understand an independent sample t-test. The research question I have is whether there is a difference between the average mileage per gallon between the cars made in Japan and those made in the United States. You can see here in this data set, I have two variables. The first variable is where the car is made. This is a qualitative variable, dichotomous to be exact. It has two values. One stands for cars made by Japanese companies, and 2 stands for cars made here in the US. Okay, and the second variable I have here is the mileage, the measure of mileage, which is a continuous variable. So if I want to change one to nominal, that's the type makers of the cars, and the other one is continuous. In SPSS, it says scale, which stands for quantitative variables. The first step before we run any analysis is to get the descriptive information. Keep in mind that for different type of variables, we have different ways to obtain their descriptive information. For example, the maker of cars, which is a qualitative variable. Even though I have 1 and 2, maybe I can have 3 for their different values. Those numbers are simply numeric labels. They do not have logical orders. So you do not want to get things such as mean, median, standard deviation, variance for their descriptive information, because simply you cannot rank the values. One is lower, 2 is higher. So for qualitative variables such as the car makers, we can go get the descriptive information here. You go to Analyze, Descriptive Statistics, Frequencies, and you bring the variable to the right. Make sure you display frequency tables. Also, you can ask for information such as what's the minimum value, what's the maximum value. And if you want to have some kind of visual display of the distribution for this type of variables, you can go to this place called Charts. And for qualitative variables, which include nominal and ordinal variable, you can ask for bar charts as well as pie charts, but you can only ask for one at a time. So I'm going to do the bar chart at this time just to show you the frequency of the distribution. Okay, and once you're here, you click OK. And in the output file, you can see that there are 80 cars in the sample that are Japanese cars, and 79 of the sample, they are US cars. And there's a slightly difference in the height of the two bars, because this one has a frequency of 80, this next one has a frequency of 79. Okay, now go back to our next variable, which is the mileage reported by each of the car owners. What's the average mileage per gallon? And this is a quantitative variable. So for this type of variable, we can get descriptive information from the same place. We go to frequencies, but in addition to those simple measures, we can ask for more measures of central tendency. We can ask for mean, median, and mode. And for the measure of variations, in addition to maximum and minimum values, you can ask for standard deviation, variance. Since this is a continuous measure, which you have many possible values, the display of frequency tables doesn't really help in any way. So we are going to uncheck this place and see what we get once we click this button OK. But similar to the descriptive information for the qualitative variable, we can ask for some visual display of the frequencies. So for quantitative variable, the best choice is the histogram. And if you want to say if the distribution follow a normal curve, you can ask for a normal curve to be displayed on your histogram as well. So let's see what we get by doing this. You can see that we have 159 valid values for this particular variable, and the mean of those 159 measures is 23, and the median is 22 with a mode of 14. And this variable has a standard deviation that's close to 8.45. The maximum value is 39. Compare that to the minimum value of 9. And here you see the distribution of all the 159 values. Here that's the minimum 9, and that you have some cars that has a mileage per gallon close to 40. And the distribution of the variable do not really follow a normal distribution. As a matter of fact, this variable mileage seems to follow a bimodal distribution, with one mode that's close to 15. We know we have a mode of 14, and another mode that's somewhere around 32 or 33. With the knowledge about the descriptive information for the two variables, now we are ready to run an inferential test. We know we have two independent samples. To compare their average mileage, we need to do an independent sample t-test. You can go here, that's called Analyze, and find a place that's Compare Means. And here you see we have an option that says Independent Sample t-test. Our test variable, it's the term used by SPSS to stand for the dependent variable, is the quantitative measure of mileage. The grouping variable is the term used by SPSS for the independent variable. So we have the two car makers, they are coded as 1 and 2. So we put the values in there, and nothing else is really necessary. As long as you click on OK, you are given the output. By default, you actually are provided with the descriptive information that shows you how many in each of the two groups, what's the group mean, and standard deviation with regard to the dependent measure. Here's the mileage. So we have the average mileage for Japanese cars at around 30 miles per gallon, and for US made cars it's around 16 miles per gallon. And here is the standard deviation within each of the groups. Okay, and the independent sample t-test, first we need to pay attention to this part. This checks whether we meet assumption of equal variance across groups. If we meet this equal variance assumption, we read the first line that says equal variance assumed. If in the case of we violated this assumption, we have to read the second line. In here says equal variance not assumed. Okay, this is a test for equal variance. Let's see, we use alpha equals 0.05. That's the level of tolerance we have for making a type 1 error. This p-value, the significance p-value, 0.002, is lower than alpha equals 0.05, which means we need to reject the assumption of equal variance. We do not meet the equal variance assumption, so we have to look at this line, the second line. Based on the output it shows here, the observed t-value is 17.97, and the degree of freedom is somewhere around 147. If you compare the two means, 30 versus 16, the chance for you to observe such a difference when the null hypothesis were true is lower than 0.001. The null hypothesis we're testing here is that there's no difference between the average mileage of the Japanese cars and the US cars. So mu1 equals mu2 is our null hypothesis. Now we know that the populations of Japanese car owners and the population of owners of US cars, both are extremely large. We only took around 80 from each population. So that's a very small fraction of the entire population. So when we try to make an inference about the entire population based on such a small fraction, such a small sample, we need to keep in mind that we can take many of different samples from the population. Each sample we take will have a difference between the two sample means. And the difference between the two sample means, if the null hypothesis is true, if in fact the two populations have no difference, will be most likely to be close to 0 when you compare two sample means. However, the chances are that we can have such a good luck, we get extreme values that's very strong difference between the samples, even though in fact the two populations has no difference. So that's come here the sampling distribution of all possible differences between the samples means we take. Out of the millions of samples we could take from the two populations, what's the likelihood, what's the probability for us to observe a difference as strong as 13.81? The probability is lower than 1 out of 1,000 such samples. So we have a p-value that's lower than alpha equals 0.05. We're going to reject the null hypothesis and conclude that there is a significant difference in the average mileage of Japanese and US made cars.